My name is Ruoqing, and I'm from the King's College London. I'm the first year student, PhD student. So my topic's about cost reduction potential of carbon dioxide removal using bipolar membrane electrodialysis. So here's the table of contents of the overall presentation. And according to the latest IPCC report, the total net anthropogenic greenhouse gas emissions still remain very high and continue to increase from 2010 to 2019. And carbon dioxide removal is crucial for helping to meet the climate target set in the Paris Agreement. And the CDR is a method to capture CO2 from the air and store durably, which can deliver the negative emissions. And in the next century, CDR plays three major functions. So in the near term, to reduce net emissions, and in the medium term, to offset unavoidable emissions from hard-to-abate sectors, thereby enabling the achievement of net zero emissions. And then in the long term, to achieve negative emissions if the removals are larger than the emissions. So what are the current CDR methods so far? And here shows the main CDR technologies, and it can be classified as two categories. One is the conventional CDR technologies such as afforestation and restoration, which basically you plant trees to capture the carbon dioxide, and then the soil carbon capture, sequestration, and biochar. And those conventional CDR technologies has been well developed and scaled up. But at the same time, there are other CDR technologies such as novel CDR technologies that are at a very early stage of the development. So such as direct air capture and storage, which use a chemical process to capture carbon dioxide from the ambient air and then storage permanently. And also such as the bioenergy with carbon capture and storage, or the enhanced weathering and ocean alkalization and ocean fertilization. So if you compare the costs from the conventional CDR technology with the novel conventional CDR technology, we find the novel technologies so far are still very expensive, especially for the DAC systems. They are the most expensive technology so far. And there is an engineering system that can be used for different type of CDR technologies, such as it can be applied in DAC, direct air capture, or ocean alkalinity cycling and ocean alkalinity enhancement. And they have the advantages of other CDR technologies, such as it can be run completely by the renewable energy, and it has the modular design, which means it has the cost reduction potential once the system has been massively produced and scaled up. And also compared with the reforestation, it requires minimum land area. But since this technology is at the early age of the development, it has a very high cost and high energy consumption. And at the same time, it's very small scale. So in this project, we aim to look at the cost aspect of the BPM-ED CDR technology. And if we look at the clean energy sector, we may see the solar and the wind technology has experienced a cost reduce over the past decades. And learning curve is a tool that are readily used for analyzing the cost reduction for the clean energy and to inform the energy policy decisions. And learning curve is to describe the relationship between the cumulative production and the cost. So there are some cost reduction factors can be identified from the learning curve tool, such as the learning by doing, learning by researching, learning by deployment, learning by using, and the experience spillovers. We wanted to analyze the BPM-ED CDR, but since the technology is very early stage and there isn't much data from it, so we decided to analyze the PV-ED first, because they have synergies between these two energy systems, and it's feasible to transfer the learning from the PV-ED to identify the cost reduction factors for the BPM-ED CDR systems. And so in this study, we aim to preliminarily assess the potential of flexible BPM-ED technology for CDR cost and emission reduction through developing and analyzing the learning curve of PVED. And secondly, to assess other contributor factors such as learning by doing and others to estimate future cost reduction of the proposed BPM-ED-based CDR system, by transferring the learning from PVED to BPM-ED system. So moving on to the BPM-ED mechanisms. So it utilizes the electrodialysis process as a base unit, but what difference from it is the utilization of a bipolar membrane, which consists of a cation exchange layer, an anion exchange layer, and a water splitting interface, where it can produce the hydrogen ions and hydroxide ions, which can further produce acid and base. And this is critical for the carbon capture process. So to initiate the process, we need to introduce a carbon dioxide rich source on one side of the membrane, and a pH gradient created across the membrane proposes the movement of bicarbonate ions and carbonate ions. So the figure 2 shows the most commonly used BPM-ED cell configurations. So basically, the BPM AEM and BPM is one of the most commonly used, and also the BPM CEM and BPM is another two configurations. And here the figure shows the overall process of BPM-ED-based CDR processes. And so for the direct air capture process, we use the air contactor to absorb the carbon dioxide from the ambient air, and then the BPM-ED unit will produce the alkaline such as potassium hydroxide to react with the carbon dioxide and produce potassium carbonate and potassium bicarbonate. And then this is an alkaline loop. But at the same time, it can generate an ice solution, which will go through the gas separation tank to strip out the carbon dioxide. And then the carbon dioxide depleted ice solution will recycle back to the BPM-ED system. And unlike the DAC process, the ocean alkalinity cycling and ocean alkalinity enhancement is to indirectly capture the carbon dioxide from the seawater. So seawater as the input into the BPM-ED system, and then it will have 3 streams generated. One is acid, one is partially desalinated seawater, and base. So the acid will combine with the desalinated water to pass through the membrane contactor, where it can strip out the carbon dioxide, and then resulting in a low pH, low TA, and low DIC content of the solution. And then we use the base produced from the BPM-ED unit to neutralize the resulting water. And then this will return back to the ocean to absorb more carbon dioxide. And similarly, the OAE process is very similar, but it does not use the acid process produced from the system. It's more like a byproduct. So the base will combine with the partially desalinated seawater, and then it will increase the pH and total alkalinity, which will go back to the ocean and absorb more carbon dioxide. So moving on to the methodology we use to analyze the cost of the PVED system. So in our learning curve approach, we have 3 indicators. One is the cumulative production, the levelized cost of water, and patent counts. So those first two indicators are collected from the research paper, and the patent counts are from the patent scope database. And we did 2 one-factor models, one for learning by doing and another one for learning by searching. Since one-factor model cannot reveal the relative cost reduction for each of the factors, we also did 2-factor models. So here shows the one-factor model for the learning curve model, and this is the 2-factor model. So for the results we get from the PVED system, in the one-factor model, the learning by doing accounts for 46% of the cost reduction, and then learning by searching accounts for 41%. And in the 2-factor model, we can see that learning by searching actually accounts for more for the cost reduction. And in fact, the learning by doing, learning by searching, and the economic of scale are the high-level cost reduction factors. And the previous research have identified some of the low-level cost reduction factors. So let's attribute that to the high level. So let's take solar panels as an example, since it's a very key component of the PVED system. So for the low-level cost reduction factors, the material cost, module efficiency, and the yield, they are the low-level cost reduction factors. And the learning by doing rates could account for 12% due to the yield increasement. And then R&D could account for 60% because of the improvement on the module efficiency, wafer size increasement, and etc. And we also use this to analyze the PVED. Since we collect the data from the research paper, so it's actually limited in the academia area without consideration of the industrial. So the learning by doing could be due to the iterative improvements through the overall research on the PVED. But at the same time, the innovation could be due to the different methodology we developed for reducing the battery resilience to decrease the capital cost, where we increase the flexibility of the PVED load to reduce the energy consumption. And those could be attributed to the innovation. But in this model, there are some limitations, such as we use the historical data, which means it cannot guarantee the future trend could follow the same pattern. And also the limited data and discontinuity could affect the result accuracy. So to transfer the learning from PVED to BPM ED-CDR, here we shows the current research on the BPM ED-CDR in terms of the capacity and the capital and the cost. So here we can see the commercial plants aim to reach capacity between 50 to 100 megaton CO2 per year with a cost of $100 to $300 per ton of CO2. And also co-locating the BPM-ED plant with the desalination plant could significantly reduce the cost. And then the base process could be cheaper than the acid process. And also, we can also see the BPM-ED system for post-combustion is much cheaper than the CDR process. And this table shows the electrolysis commercial membrane stack design. And here shows the BPM-ED commercial membrane stack design. What I want to say from these two tables is these two systems have the shared units in terms of the membrane material stack design, and also they have the shared manufacturers. So not only they can produce the same manufacturer can produce ion exchange membrane, but also the bipolar membrane. So it's feasible to transfer the learning from PVED to the BPM-ED CDR in both low and high level cost. And for example, if we can increase ion exchange membrane market size, it's very feasible to benefit both of the system, and that can be attributed to the economic of scales. And also membrane folding and scaling is a major limitation of the scale up of both of the systems. So if the membrane performance can be enhanced, and that could be, in the future, it's feasible to reduce the cost because the innovation. And also if we can increase the production of the components of the two systems, through the learning by doing, like you gain the experience and the cost will be reduced. So here is the conclusion. The BPM-ED CDR is vital for climate goals, but face challenges. And in the one-factor model of PVED, the two factors we selected are contribute quite similar. But if we look at into the two-factor model, the learning by searching plays a major role in the cost reduction. And the synergies with PVED can reduce BPM-ED CDR costs through transferable learning, early stage benefit from the learning by searching, and long-term impact from learning by doing as the technology matures. Understanding these factors is in cost-effective CDR solutions and accelerate the net zero transitions. So that's all. Thanks for listening.
Anyone? Yeah, sure. So it's the learning clusters here. It's only just for the core process. And for the whole real separation also the time. It's always actually there's something mostly it's nice. Over inside of the nothing else eating fire and poultry. That was my idea. All other sorts of technology that we already have developed well, so most of that are already right. So modeling can be looking at hypothesis or differently we can really say
So we are looking at the overall process, but in here we did not do a learning curve on the BPMED CDR system, but instead we do a PVED system is a electrode that it's used for the water desalination process. We wanted to learn from because these two systems has very similar units and materials. So we want to learn from PVED to the BPMED CDR. So that's not really for doing the learning curve of the BPMED CDRs.
any further questions? Thank you very much one more time. And we will move to the next